Now that we've learned so much about Taylor series, this section we're going to be working with Taylor series in terms of evaluating functions, looking at limits, and rewriting some things. So to get started, remember that for a Taylor series to be able to exist, or if you want to be able to work with a series, you have to make sure that I can take the derivatives of the function and evaluate them at the center c equal a. Now it could be anything for the center. In this particular case I said a. But if you want to evaluate something like the cosine of 2 or e to the negative 0.5, then what I would do to evaluate these is I would look at the Taylor series and I would evaluate them at, for the first one, x equal 2 if the series is centered at 0. Now for my second one here, I would take my Taylor series and evaluate it at x equal negative 0.5 if the series is centered at 0. So that's a couple things that we can do with series. Next I want to look at taking limits using these series. So usually we have some very difficult to look at functions, and then what I want to do is simplify them using Taylor series and then take the limit. And a lot of times it's a lot simpler because I'll be using polynomials instead of square roots, natural logs, trig functions, things like that. Now in order to work with most of these, we need these shortcuts to these Taylor series that's provided in a table. Now this table is sometimes provided in homework problems, sometimes not. So it's on your formula sheet. You definitely don't need to memorize these, but have them on your formula sheet so you'll be able to use these. So these are Taylor series. Now we're going to be using these when we work the rest of these problems. So it's nice to be able to have one at hand so we don't have to scroll up and down all the time. So the first problem we're going to look at, we're going to use some substitutions from this table. And again, we're going to refer back to this often. So we're looking at the limit as e to the x minus 1 over 2x. Now if we took this limit directly, and instructions are here to use the series to evaluate this, but if we were to take this limit directly, I'd get 0 over 0, which is indeterminate. In fact, it's indeterminate L'Hopital's. So I should be able to use L'Hopital's rule on this. If I did that, I'd get e to the x over 2, and then e to the 0 is 1 over 2 is 1/2. So I know the limit here is 1/2. So sometimes I can use some different methods, but they're asking us to use series so we can learn that skill. So let's go ahead and use series here. So first of all, what I want to do is I want to substitute in for this e to the x. So if you look on your sheet up above, we know that e to the x is equal to the series 1 plus x squared over 2 factorial plus, and then it has dot dot dot, but we can extend this out, x cubed over 3 factorial, x squared over 4 factorial, etc. So what I can do then is when I take this limit as x approaches 0, e to the x I can rewrite as 1 plus x squared over 2 factorial. I don't have to write out too many of these terms, but I have to write out enough so I can see the pattern. So that's my e to the x, and then minus 1. That comes from right here. And this is all over 2x. So right now I don't think we're really ready to do too much with this in terms of taking the limit. We want to do some simplification here. The 1 and the minus 1 cancel, and I'm left with the limit as x approaches 0 of x over 2x, because this 2x goes underneath each term, plus x squared over 2x times 2 factorial, plus x cubed over 2x times 3 factorial, plus x to the 4th over 2x times 4 factorial. So this is going to be equal to the limit as x approaches 0. As I simplify, x over 2x would leave me with 1 over 2. Next one, I would be left with x over 2 times 2 factorial. Next I'd be left with x squared over 2 times 3 factorial. And you're seeing the pattern right here as well. So x cubed over 2 times 4 factorial. Well, if we look at the limit right here, as x approaches 0, then what happens, all of these terms go to 0 because I have 0 over some sort of a constant, and so that would go to 0. So all I'm left with at the end is 1/2, and so that's my limit. Now again, we could also find this using L'Hopital's, but they want us to use the series so we get used to this substitution with this transcendental numerator and linear denominator to be able to take the limit easier. So more than one way to take these, but the point is you always have to make sure you show your work so I know what method you're using. Now as we continue to work on these next sets of problems, remember we're going to constantly be referring back to this table at the top, so make sure you have your table with you while you're watching the lecture. It should be in your guided notes, and you can also print out a copy. So we're going to be referring back to this all the time. Okay, so for our next one, same thing, evaluate the following limit using Taylor's series. It looks like to me we could take this piece and rewrite it. Now if you look at your table, there's actually a function rewrite for a Taylor series of minus natural log of 1 minus x. So I have to take the minus sign with it, so all of this goes. And if we look on our formula sheet, that would be x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, etc. So now when I look at this, when I take my limit, and I guess we should take a limit right away, I'd get 0, natural log of 1 is 0, so I get 0 over 0, which is indeterminate L'Hopital, so I could start taking derivatives. But you can see that this might get a little bit ugly when we take the derivative of this piece, and I do my 1 over u prime, and then we have some layered fractions. So you could probably come up with your solution using L'Hopital's, but we're going to use series here. Okay, so I have my minus x, and then I'm going to have a plus sign. Now the reason I have a plus sign is this entire minus natural log of 1 minus x is this, if you look on your sheet. So that's going to be x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 dot dot dot. And this is all over 8x squared. Well, right away I see that the negative x and the plus x can cancel, and I'm left with the limit as x approaches 0 of x squared over 8x squared times 2 plus x cubed over 8x squared times 3 plus x to the 4th over 8x squared times 4. And of course this is dot 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 dot. So we want to simplify this. So I have the limit as x approaches 0. The x squareds cancel here, and I'm left with 1 over 16. And then my next term, I have to keep simplifying here. I get x over, because I have x squared or x cubed on the top, x squared on the bottom, over 8 times 3, plus x squared over 8 times 4. So you can kind of see the pattern here, and I guess for the 16 we could have written that as 8 times 2, and then you can really see the pattern here. Now as x goes towards 0, these terms go towards 0, and I'm just left with 1 over 8 times 2, which is 1 over 16. So that's my limit here. So these problems really aren't all that complicated. The concept, I guess, is a little complicated, but the actual applied part of it is algebra. Now when we're working these problems, it's really just substitution and simplification. So the only thing that really changes here are the functions that we're using. So for this problem we're using natural log of 1 plus x. That's what we want to find the Taylor series for. So if you look on your Taylor series sheet, the one that's at the beginning of this lecture, I have the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And the x to the 4th over 4 is not actually on that Taylor series sheet, but you can see what the pattern is and fill it out. Now if I took this limit right away, I would get 0 over 0, which is indeterminate. It's indeterminate L'Hopital's. So I could start taking a derivative of the top and a derivative of the bottom and applying L'Hopital's to try and figure this out. But this one says to use Taylor series, so I'm going to do that. But no matter which method you use, you should come up with the same answer. So let's look at the limit as x approaches 0. And the natural log of 1 plus x is rewritten as x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Okay, and then I have this last two terms, minus x plus x squared over 2. And this is all over that denominator of 4x cubed. So right away we see some canceling occurring. So I have x and a minus x, negative x squared over 2 and a positive x squared over 2 is leaving me with the limit as x approaches 0. And it looks like we're left with x cubed over 4x cubed times 3 minus x to the 4th over 4x cubed times 4. And again, the whole idea here is to simplify. So I still have the limit as x approaches 0. The x cubes cancel on this first one. I'm left with 1 over 4 times 3. For my next one, I'm left with an x on top, and I have that over 4 times 4. And of course, this goes to 0 because my limiting value is as x approaches 0, and I'm left with 1 over 4 times 3, which is 1/12. So again, if you had to use L'Hopital's, you'd get the same answer. Might be a lot more work though. So next problem, just like the last, we're going to be doing some substitution. This one is an inverse trig function, and I do have a variable out front, so I'm going to have to keep track of that as well. This is actually not the right problem. Let's see if we can find the right one. Okay, here we go. So this one's actually a multiple choice. I'm not going to put down all the multiple choice options. We'll just work it as is. So this one says evaluate the following limit using Taylor series. So we could again take that limit right away. This is the limit as x approaches 0. The inverse tangent of 0 is 0. So in the numerator I get 0. The denominator I get 0, which is indeterminate L'Hopital's. But remember, to apply L'Hopital's, I'm going to have to be taking a lot of derivatives here. And then when I start taking the derivative of inverse tangent, things get a little complicated. So the hope is that I can rewrite the inverse tangent of x with its Taylor series and make this problem a little bit easier. Well, go ahead and look on your formula sheet for your Taylor series, and you get inverse tangent is equal to x minus x cubed over 3 plus x to the 5th over 5, and then following that same pattern, minus x to the 7th over 7. So when I take this substitution and I take my limit, I have to have a 3 out front of this inverse tangent. So that's going to be 3 bracket x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. And then the second part, I have to go minus 3x plus x cubed. If a mistake is made here, it's usually to not subtract out that next piece. And this is also all over 2x to the 5th. So let's go ahead and rewrite this using the limit as x approaches 0. So I have 3x minus x cubed because the 3's cancel, plus 3/5 x to the 5th minus 3/7 x to the 7th minus 3x plus x cubed. And this is all over 2x to the 5th. And right away we can see that the 3x's cancel and the minus x cubed cancels with the positive x cubed. And this leaves me with the limit as x approaches 0 of 3x to the 5th all over 5 times 2x to the 5th minus 3x to the 7th all over 7 times 2x to the 5th. And of course this pattern would continue, but I'm going to simplify this. So let me see here. I get x to the 5ths cancel, and I'm left with 3 over 5 times 2. And then over here I'm left with 3x squared all over 7 times 2. Now right away the second term will go to 0 because I'm taking my limit as x approaches 0. In my first term I'm left with 3 over 5 times 2. And of course 3 over 5 times 2 is equal to 3 over 10. And that's my solution. So again, these are These are kind of fun problems. Same instructions. Evaluate the limit using Taylor series. Now the Taylor series we're going to want to look at here, we're going to have to do a little simplification first. So we want to use the sign of 6x. Well, I don't have the sign of 6x on my sheet. I have the sign of x. So if you look at the sign of x on your sheet, that's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then following that same pattern, minus x to the 7th over 7 factorial. Now, because this is sine of 6x now, I have to rewrite, and everywhere I see an x, I'll put a 6x. So that's going to be 6x quantity cubed. It has to be in parentheses. 6x quantity to the 5th, and then 6x quantity to the 7th. So again, make sure that you don't have 6x to the 5th written like that. You need to have the parentheses here, because this is equal to 6 to the 5th x to the 5th. If you wrote 6x to the 5th, that's equal to just 6x to the 5th. The 6 doesn't get raised to the power, so you have to write it correctly. So let's go ahead and use this to substitute in. Again, if you took your limit right away, you would get 0 over 0, which is indeterminate L'Hopital's, and you could start applying L'Hopital's, but we're going to be using Taylor series here. So I have 18x minus 108x cubed minus 3. And now, in place of the sign of 6x, I'll go ahead and put all my terms in here. I'll have 6x minus the quantity 6x cubed over 3 factorial plus the quantity 6x to the 5th, 5 factorial, minus the quantity of 6x raised to the 7th over 7 factorial. Of course, that pattern continues on. And this is all over 3x to the 5th. So I have the limit as x approaches 0 of 18x minus 108x cubed. And I'm going to go ahead and distribute the minus 3. If I do that, I'm going to get minus 18x plus 3 times 6 cubed x cubed over 3 factorial, which would be 3 times 2 times 1. Okay, minus 3 times 6 to the 5th x to the 5th all over 5 factorial. And I'm just going to write it as 5 factorial. And I also need to include this denominator here. So that's 3x to the 5th over under each one of these. I'll just write times 3x to the 5th here, 3x to the 5th here. And my next term then would be minus 3, 6 to the 7th, x to the 7th, all over 3x to the 5th times 7 factorial. So this has been simplified in terms of the distributions, but I do need to simplify this in terms of canceling. So here, these two terms cancel. I shouldn't say they go to 0, they just cancel. And then it's not really clear what's going to happen here with this term, but it's going to cancel too, but we'll go ahead and write it out. All over 3x to the 5th plus, then I'm going to have these 3's cancel, and then I have 6 times 6 times 6 is 6 cubed, and in the denominator I have 2 times 3x to the 5th. So if I cancel the 2 into the 6, I get a 3. And I'm just going to leave the x's as is for now. Let's go ahead and look at my next term. So here I have 3 times 6 to the 5th all over, the x to the 5ths cancel here. That's interesting. So 3 times 5 factorial. Now my next term, we're going to go 3 times 6 to the 7th, and I'm going to be left with x squared on top because I have x to the 7th over x to the 5th, 3 times 7 factorial. I think I have a mistake here in my second term, so let me take a check at it. And I don't have a mistake, but what I was worried about is my higher power is in the denominator with my x power, But luckily these cancel, so I don't have to worry about that. Otherwise I would have had a 0 in the denominator, it'd be undefined, but they canceled, so I don't have that term. So now we're left with the limit as x approaches 0. Now this term is going to 0 because I have the highest power of x on top. So I'm left with minus 3 times 6 to the 5th. And I'm actually going to write that out. 2, 3, 4, 5. 1, 2, 3, 4, 5. There's my 6 to the 5th. Over 3 times 5 factorial, which is 5, 4, 3, 2, and then you don't have to write the 1, but it is there. So let's start canceling. So the 3's obviously cancel. I will have the negative, so don't forget the negative. 3 times 2 cancels with one of the 6's on top. Let's see what else we can get to cancel. 4 would reduce to 2, 6 would reduce to 3, and then this 2 would reduce another one to 3. So I'd be left with negative 6 times 6 times 3 times 3 all over 5. So I'd have 108. 6 times 6 is 36. 36 times 3 is 108. And 108 times 3 is 324, and it's negative 324 over 5. So that's my limit. So lots of simplifications there, and you can kind of decide how far you want to go with some of those before you actually evaluate them. This problem has a little bit different instructions. They want us to evaluate a function sine at -2, and we're thinking -2 radians here. So it says use an appropriate Taylor series to do this. Well, let's find the appropriate Taylor series to start with. So if you look on your Taylor series sheet, we know that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then following that same pattern, minus x to the 7th over 7 factorial. Now it says the first 4 non-zero terms, so I see here 1, 2, 3, 4 terms, so we're good to go. So what I do here then is I plug in a -2 for each of these. So I have -2 minus a -2 cubed over 3 factorial plus a -2 to the 5th over 5 factorial minus a -2 to the 7th over 7 factorial. Okay, so let's go ahead and look at these terms. Again, it wants the first 4 terms. So as we simplify, I get a -2, so that's easy enough to look at. Now, -2 quantity cubed would be a -8. -8 times a negative out front would be a +8, and then 3 factorial is 3 times 2. Okay, let's keep working. 2 to the 5th would be 2, 4, 8, 16, 32, so it would be a -32 over 5 factorial, which is 5 times 4 times 3 times 2 times 1. And then over here, 2 to the 7th, 32, 64, 128. So this would be a +128 because I have the negative sign out front, over 7 times 6 times 5 times 4 times 3 times 2 times 1. So we need to simplify this first before we can actually say these are my first 4 terms. So easy ones are coming up here. The 2 cancels into the 8. Let's see what else we have. We have 4 would go into a -32, -8 times. 8 times 4 is 32. And then 2 would cancel into the 8, -8, -4 times. So there I'm left with -4 over 12, it looks like to me, or sorry, -4 over 15. Okay, 128. So we don't have to always take the biggest number. Let's just go ahead and see if we can start with something here. Let's see, 10, 11, 6 won't go, 5 won't go. I think 4 will go, so let's go ahead and do 4. 4 would go into 128 32 times. 2 would go into 32 16 times. Now 3, 5, 6, 7 do not cancel into 16. So I'm ready to quit canceling and to write out my first 4 terms. So it would be a -2 plus 4/3 minus 4 over 15 plus 16 over, let's see what we have here, 6 times 5 is 30. 30 times 3 is 90. 90 times 7, 9 times 7 is 63. 630. We might be able to get that to reduce a little bit more. Let's have a look at that. Yeah, 6 doesn't go into 16, but they're both even, so I could cancel there to just get a slightly smaller number. So then I'd be left with 8 in the numerator. In the denominator, I'd have 5 times 3 is 15, 15 times 3 is 45, 45 times 7 is 315. So those are my first 4 terms. Now if I said my first term was 2, I'd be wrong. It's negative 2. My second term is 4/3. My third term is a negative 4/15, and my fourth term is 8 over 315. So don't forget to take the signs with you when you talk about your terms. Now sometimes you'll see this written as plus a negative 4/15, and that's okay. Either way, that's equivalent. Let's do the same for this one. We're trying to estimate natural log of 2 by looking at the first 4 non-zero terms. Well, we don't have a formula for the natural log of, let's say, just x. We have the natural log, if you look on your formula sheet, of 1 plus x. So the natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus, and of course we can follow the pattern here. Now what I have here is a 2, so I need a 1 plus 1 here. That means x had to equal 1 in order for this to happen. So x had to equal 1 right here. So when I substitute back in here, everywhere there's an x, I'm going to put in a 1. So I have 1 minus 1 squared over 2 plus 1 cubed over 3 minus 1 to the 4th over 4. Now notice we're not taking the 4th power on the negative sign, just the 1, so you have to be real careful about that. So let's go ahead and rewrite then. So we have the natural log of 2 is equal to 1 minus 1/2 plus 1/3 minus 1/4. Those are the first 4 terms. The first term is a positive 1. Second term is a negative 1/2, and remember you can write that as plus a negative 1/2 if you want, but those are my terms. So that's another application of Taylor's series. For the next problems, we're going to do something a little bit different. So I want to put this table in here so we have it right in front of us, and then I'll go ahead and pop the question in next. Now what we're asked to do here is identify the function that this is coming from. So we're looking at the series, and so we're looking down this column right here, and we're trying to guess back to what does this come from. Does it come from inverse tangent, minus ln, that type of thing. Now in order to figure that out, we're going to have to be able to identify this series as one of the functions over here. Now the problem is it's not going to be exact, so sometimes I'm going to have to rewrite some things here. So I definitely see I have a negative 1 to the k here. So it could be this one because I have that negative 1 to the k. Where else do I have that? I have a negative 1 to the k here. That's a k plus 1. Here's a negative 1 to the k. So it's going to be one of these. Now the next thing I want to look at is I have a 3 to the k. Well, I can throw this one out because there's no k in the exponent in the denominator. No k to the exponent in the denominator. No k in the exponent in the denominator. And then we might look at this and go, well, wait a minute, there's no denominator here at all. But let's go ahead and do a little rewriting. So let's look at k equals 0 to infinity of negative 1 to the k. And then let's look at this as x squared over 3 quantity to the k, because I can rewrite that. I can combine those underneath the 1 exponent. Now the only way that I can do that is if I write the x squared in the parentheses. So now when I look at that, this is definitely what we're looking at here. So if that is my rewrite, then what I have here then is that my x is equal to x squared over 3. I replace it with that. So the function that comes from is 1 over 1 plus x. But remember, I just said that x is actually x squared over 3. Now rewriting, I'm going to find a common denominator here of a 3 in the denominator, and when you divide by a fraction you multiply by the reciprocal, so this flips. So I'm left with 3 over x squared plus 3. So that's the function that this series notation comes from. Okay, so this is the power series that comes from. So sometimes a little trial and error, process of elimination and rewriting. Sometimes it's really straightforward though. I've put the table up here again so we can use that process of elimination. So start with a clean table. So I'm looking for a series that goes from k equals 1 to infinity of x to the k over k. So we're starting 1 to infinity. Oh boy, it's right here. So I don't even have to do a rewrite. So that's my only option right here. So if I do that, it looks like to me that this is just equal to exactly what that function is, and that's minus natural log of 1 minus x. So there's nothing I need to rewrite here. It's already in the exact form. It's already x to the k over k. So that one is pretty straightforward. Hopefully this last one that we're going to be looking at is a little more difficult. So let's use that table and have that process of elimination again. So I'm going to put the entire table up. And we won't need most of it, but it's okay. It's better to have too much information than not enough. So last problem here. So it says use the Taylor series to evaluate the following limit. Express the result in terms of the parameter. Okay, so we have the limit of a to the x minus 1. So a to the x, that's one that we'll be able to look at here. This is this piece right here. So I can take this and rewrite it. So what I will look at here is I have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. But I want e to the ax. So that means that I'm going to take x and replace it with ax. So this is 1 plus, instead of x I have an ax, plus not ax squared but ax quantity in parentheses squared over 2 factorial, plus not ax cubed but ax quantity cubed over 3 factorial. So now as we rewrite this, I have the limit as x approaches infinity of e to the ax, which was the 1 plus ax plus, I'm going to go ahead and rewrite this as a squared x squared over 2 factorial, which is just 2, plus a cubed x cubed over 3 factorial, which is just 3 times 2. Now all of these are over x in this denominator from up here. So I'm going to pop an x in each one of these. Now let's go ahead and simplify. So I have the limit as x approaches 0 of 1 over x plus ax over x is just going to be a. And then I'm going to have a squared x, because the x squared on top cancels with 1 on the bottom, over 2, plus a cubed x squared over 3 times 2. And I have a problem here. What's my mistake? I don't know if you remember back in the other problems I said if somebody makes a mistake, it's usually because they forget that last term, and that's what I just did. Remember, there's a minus 1 on the end from the problem right here. So this will be a minus 1 over x. And then these cancel, which is good because I can't take the limit of 1 over x, I'd get undefined. So I'm left with the limit as x approaches 0. And then as x approaches 0, these terms go to 0. And I'm just left with a, and the limit of a constant is just a constant. So the limit here is a. So these are pretty straightforward little problems, Calc 2 concept, but really I'm just using algebra to solve all of these. So I hope you enjoy this section. It's a little bit shorter than most, and the problems are pretty fun. As usual, if you have questions, please let me know. I'm always happy to help.